All right, we're back. We're on page 5 of note 16, and we're talking about definite integrals. We're talking about using the fundamental theorem, and now what we're going to do is we're going to talk about using U substitution. So U substitution is a big deal when we're finding antiderivatives, equally big deal when you're finding definite integrals using the fundamental theorem. So there's two approaches to this, and I guess as we go forward, you'll see I have a preference, but my preference is not necessarily the best thing to do. So when you do U substitution, there are two options. The first option is just do an indefinite integral. So I will do an indefinite integral. I'll use U substitution. I'll find an antiderivative. Once I have the antiderivative, I go back to the original problem and I use the original bounds. So that's what I like to do. I like to do an indefinite integral. And then, so that's, I mean, it's in the notes here. I like to do an indefinite integral, evaluate it, find the antiderivative, then go back using the fundamental theorem. The way that I want to say like College Board seems to prefer is for you to make a choice of U, change everything to U, including the bounds, and then just do your new integral. And that's totally fine. It's usually actually easier. The thing that I don't like about it is that if I get the bounds wrong, that's like a mistake I didn't need to make. And so I tend to shy away from that, but let's see what it means to just change the whole thing. So we're not actually doing these. Maybe I'll evaluate. We are doing these. Okay, so we're going to use U substitution. So I'm going to say that U is equal to 1 plus 2x. And then if U is equal to 1 plus 2x, then 1/2 du is dx. Like all the rules apply for indefinite. But you also have to change the bounds. So when x is equal to 4, U is equal to 1 plus 8, so 9. And when x is equal to 1, U is equal to 1 plus 2, so 3. And then this becomes 1/2 the integral from 3 to 9 of, let's make it, so it's 1 over U to the 1/2. Let's make it U to the negative 1/2 du. Change the bounds. Okay, so I'm going to highlight it somehow. These are the original bounds. We change the bounds. You have to change the bounds. If you don't change the bounds, you're getting it wrong. Multiple choice question, virtually guaranteed. All right, plus 1 times the reciprocal gives me 1/2. The reciprocal is 2. 2 times 1/2. So we just end up with U to the 1/2. And then 3 and 9. So square root of 9 is 3 minus the square root of 3. And that's it. So we change the bounds. We change everything to U. We do our integral. We use the fundamental theorem. Not a problem. Just make sure you're doing it right. So here, this is going to be gross. U is equal to 5x. So 1/5 du is dx. Okay. And then if x is equal to pi over 4, then U is equal to 5 pi over 4. And if x is equal to pi over 3, then U is equal to 5 pi over 3. Oh man, I'm feeling some unit circle stuff here. So this whole integral is going to become 1/5 the integral from 5 pi over, is pi over 3 bigger than pi over 4? Pi over 3 is bigger than pi over 4. So I should, 5 pi over 3 is definitely bigger than 5 pi over 4. They're in different quadrants. So I'm going to write this and then I'm going to switch the bound. I should have switched the bounds and changed the sign. But all right, so we're committed, right? Pi over 4 was on top, so 5 pi over 4 is on top. It shouldn't be, but it is by direct substitution. Pi over 3 is on the bottom. 5 pi over 3 is on the bottom. Secant squared of U du. All right, so we switch it and change the sign. Negative 1/5. 5 pi over 4. 5 pi over 3. All right, and then secant squared of U. So what's secant squared the derivative of? It's the derivative of tangent. Negative 1/5 tangent of U. We're going 5 pi over 4, which is quadrant 2, to 5 pi over 3. No, 5 pi over 4 is quadrant 3. And then 5 pi over 3 is quadrant 4. So that makes sense. Negative 1/5. All right, tangent of 5 pi over 3 has the nice tangent. It's root 3, but quadrant 4, so negative root 3. And then minus the tangent of 5 pi over 4 is quadrant 3, so tangent's positive, so -1. you're not going to get a better answer, so I'm going to leave that there as it is. How much we have to go here? Oh, a lot. All right, I'm going to do, how much have we even been doing? I don't even know. I'm going to do this one. I don't know. I'll do a couple more. So u is equal to 5x. 1/5 du is dx. If x is pi over 3, u is 5 pi over 3. If x is pi over 6, then u is 5 pi over 6. Great. So this is going to become 1/5 the integral 5 pi over 6 to 5 pi over 3 sine cubed of u cosine of u du. Now you might find yourself doing another substitution here. You could very reasonably have said that u is equal to sine of 5x. And then you would get a different integral that has the exact same value. And maybe I should have done that. U is equal to sine of 5x. Then when x is pi over 6, you get the sine of 5 pi over 6, which is 1/2. When x is pi over 3, you get the sine of 5 pi over 3, which is negative root 3 over 2. And then you go from there. It's same end result, but like might have been a better idea. But I didn't do it. So I'm going to say now in my head, I need to integrate, like if this is w, I guess, then dw is cosine of u du. So I'm going to end up with 1/5, 1/4, so 1/20th sine to the 4th of u. And again, I think it might have been a better choice to go the other way. You never know until you're like doing it, and then once you're in it, you're like, I'm committed. 1/20th. All right, what is the sine of 5 pi over 3? Sine of 5 pi over 3 is negative root 3 over 2, but to the 4th. So this is a great problem. Root 3 over 2 to the 4th minus the sine of 5 pi over 6 is 1/2 to the 4th. I'm going to check this one because I don't know. 1 over 20. And then, all right, root 3 to the 4th is 3 squared is 9 over 16. Minus 1 over 16. Okay, so that's 8 over 6. That's 1/2. Just 1 over 40, maybe? That'll be nice. Okay, so let's check these. And then, I don't know, come back in the next video and do more. Also, let me mute and unmute myself, because I like to see the little thing moving so that I know that the microphone is working, because this is the worst development in a while. All right, so integral 1 over the square root of 1 plus 2x. You should always be using the templates and just make it look exactly how it looks on the paper. But whatever, I don't do that. It's fast. It's just faster for me to type. Here, I'll do the template. Integral pi over 3, pi over 4, secant of 5x squared dx. Negative infinity. Why? Secant squared 5x. That's questionable. Because secant's not discontinuous between pi over 4. Tangent's not discontinuous. Why do you think that's the answer, calculator? What is it? What do you think this is? Integral secant of 5x squared. Secant squared, right? So 5. Okay. Is that, oh, maybe that is discontinuous on that interval. This might be a bad problem. All right, so this is a bad problem. Wow, this has survived in the notes for so long without me ever checking it. This problem you can't really do the way that I've given it to you, because there's a discontinuity of somewhere in between pi over 3 and pi over 4. There's a discontinuity of secant of 5x, so like it's not a proper integral. Can't be done. Naively, if we do it, which is what we did, if I evaluate this at x equals pi over 3, I guess, and if I evaluate this at pi over 4, I get those answers. So I get the answer that I got, but like It's not right. This is a bad problem. I need to change it in the notes. Oh, the tragedy. All right. But anyway, we illustrated the idea, I think. But this problem is more complicated than I made it out to be. So I should fix that. Let's check the last one. The last one's the one I was actually worried about. Sine of 5x. So let's see. Sine of 5x, x, pi over 6, pi over 3, 1 over 40. All right, so we got that for a reason. So the reason is, if I graph secant of 5x squared, right? That's the integrand. Fundamental theorem, we have said, function needs to be continuous on the interval from a to b. So if I change the window to pi over 4 to pi over 3, and then let me change the y-axis, I guess. Window up to like 30 or something, I guess. You can kind of, what do you need to go up to for this to like look like something? 100? There's a discontinuity. There's a discontinuity in the middle. Fundamental theorem actually doesn't apply, so that's unfortunate. So I'm going to go back to the notes. I'm gonna like make a note in the notes so that you are aware when you check this on your calculator, the middle one's not gonna work. I can't even tell you, like 13 years, no one has tried this on their calculator. This problem is a bad problem. And I may actually replace it by the time you get to these notes. I don't know. Tragedy. But we got the other ones right. So I'm gonna come back in the next video and mess around with the next bunch. And so yeah, I'll see you there. Maybe I'll fix the notes, who knows? Anyway, see you in the next one.